Next chapter, Electrostatics Part 1. Now, sometimes when you touch a metallic doorknob or any metallic object, you might experience a mild shock. We also know that when a plastic comb is rubbed against dry hair, it begins to attract small pieces of paper. When two pieces of silk cloth are rubbed against two glass rods individually, and the glass rods are kept beside each other, they repel. If one of the silk cloth and a glass rod are kept beside each other, they attract. These observations are a result of formation of charges on the surfaces of the materials caused by friction between the rubbed surfaces. These charges are said to be static because they are not moving. They are different from those in an electric circuit. The study of static charges is called electrostatics. There are two types of charges in nature, positive and negative. So, where does charge come from? Let's look at the origin of charges. Previously, we said that matter consists of tiny particles called atoms. Atoms are so small they cannot be seen with naked eyes. But scientists have managed to build up a picture model of an atom, and we can use these to explain the electrical properties of matter. The atom consists of what we call subatomic particles. To see this structure clearly, let us flatten this atom. In the center of an atom, there is a nucleus which consists of neutrons that have no charge and protons which are positively charged. So overall, the nucleus is positively charged. Around the nucleus are electrons which carry a negative charge and revolve in their orbits, also called shells. The attraction between the positive nucleus and the negative electrons keeps the electrons in their orbits. However, as you move further and further away from the nucleus, this force of attraction gets weaker and weaker. So the electrons in the outermost shells are weakly attracted to the nucleus and sometimes are dislodged. Usually, an atom has equal number of protons and electrons, so it's usually neutral or has a net charge of 0. However, the neutral charge can be changed by either losing or gaining of electrons. If an atom gains electrons, it becomes negatively charged because there are more negative charges than positive charges. And if an atom loses electrons, it becomes positively charged. These charged atoms are called ions. Whether an atom gains or loses electrons depends on the material. For example, glass atoms easily lose electrons, while silk attracts electrons much more. So when the two are rubbed against each other, the glass rod loses electrons to the silk cloth and acquires a positive charge, while the silk acquires a negative charge. It is important to notice that charges are not created. They are simply transferred from one place to another. And so, if you rub your feet against the carpet, your body attracts and dislodges electrons from the carpet atoms. Your body acquires extra electrons and you are negatively charged. The carpet material is positively charged. Then when you touch a metallic doorknob, all the charges want to leave your body and go to the doorknob in order to restore the charge balance. This creates a mild shock because nature always seeks balance, that is a net charge of 0. The electric charge is the most important property of protons and electrons. The quantity of charge is denoted as Q, and the unit of charge is coulomb, denoted as C. Objects can be positively or negatively charged. So Q can have a positive or negative value. The amount of charge in a proton is equal to that in an electron. It is just the signs that are opposite. So a proton has a charge equal to positive 1.6 times 10 to power negative 19 coulombs, while an electron has a charge equal to negative 1.6 times 10 to power negative 19 coulombs. The flow of electrons is what creates the electric current that we shall see later. When two positively charged glass rods were brought close together, they repelled. But when a positively charged glass rod and a negatively charged silk cloth were brought close together, they attracted. This is the basic law of electrostatics. Like charges repel, and like charges attract each other. Next, we look at charging bodies. So, we've seen how bodies acquire charges by either gaining or losing electrons. When rubbed, the glass rod loses some of its electrons to the silk cloth. This deficit of electrons makes it positively charged, while the excess of electrons makes the silk cloth negatively charged. This is charging by friction. Neutral bodies can also be charged using already charged bodies. There are three methods of charging: contact, induction, and separation. We start with charging by contact. Now, if we momentarily touch an uncharged polystyrene ball with a charged glass rod, the ball becomes positively charged as well. This process of charging by bringing a charged body in contact with a neutral body is called charging by contact or conduction. In this case, some electrons are transferred from the ball to the glass, and thus the glass becomes less positively charged due to the slight neutralization of the positive charge. The same positivity lost by the glass is acquired by the ball when it loses the electrons. Again, remember that no charges are lost or created, they are just transferred. And therefore, during charging by contact, the body being charged acquires the same charge as the charging object. Next, charging by induction. When a charged object A is placed near an uncharged object B, A induces an unlike charge on the near side of B and a like charge on the far side of B. We call them induced charges because they have been created by repulsion forces. In this case, the charges inside B are only polarized and no transfer of charges has taken place. This process of polarization of charge on an uncharged body, when a charged body is held close to it, is called induction of charge. For example, bringing a negatively charged rod near a neutral metal sphere, a few electrons in the metal sphere move away to the far side due to repulsion, leaving a positive charge on the near side. This charge is temporary, so that if we move the glass rod away, the sphere returns to its original uncharged state. Bringing back the charged glass rod again, we see polarization of the sphere. Now, if we add the far side of the metal sphere using a conducting wire, the electrons on the far side of the metal sphere flow into the ground. The positive charges are however held at rest by the negative charges on the rod. And when the glass rod is withdrawn, the positive charges in the sphere redistribute uniformly. In this way, the sphere acquires an overall positive charge. We use the word overall because the metal sphere did not lose all of its electrons. The number of electrons lost equal to those that were on the charged glass rod. In other words, the induced charge is equal to the inducing charge. And so in induction, the body to be charged acquires a charge opposite to that of the charged body used. Next is charging by separation. Now, we keep two metal spheres A and B supported with insulating stands and in contact with each other. When we bring a positively charged glass rod near sphere A, negative charges accumulate on the near side and positive charges accumulate on the far side of sphere B due to attraction and repulsion, respectively. Now, we separate the spheres by a very small distance, keeping the charged glass rod near them. When the glass rod is withdrawn, sphere A will retain the negative charge and sphere B will retain the positive charge. When we put them further apart, the excess charge on the metal spheres distribute uniformly, so the two spheres acquire opposite charges. The process is called charging by separation. Next, we look at the electroscope. Now, to know if a body is charged, we use an instrument called a gold leaf electroscope. It consists of an insulated metal rod with two gold leaves on one end and a metal disc on the other end. This setup is enclosed in a glass jar with the help of a tight cork, with the disc placed outside the jar. To test a material like glass rod for electric charges, the object should be brought close to the metal disc of the electroscope. If nothing is observed on the gold leaves, then the glass rod is not charged. If the gold leaves diverge, then it indicates that the glass rod is charged. The amount of diversion indicates the size of the charge on the glass rod. Charging an electroscope. We start with charging by contact. We charge a glass rod positive by rubbing it on a silk cloth. When the rod is placed in contact with the metal plate, the leaves diverge. And this is because the electrons are attracted into the glass rod, they neutralize it, and the electroscope has an overall positive charge. When the rod is removed, the leaves remain diverged, so the electroscope is charged by conduction or contact. When the plate is touched with the hand, the leaves collapse. We say the electroscope is discharged. This happens because touching acts as earthing, and electrons from the ground rush up and neutralize the positive charges on the electroscope. An electroscope can be charged negative by touching its plate with a negatively charged rod. When the plate is touched, the leaves diverge due to negative charges being repelled downwards and all the induced positive charges being neutralized by the excess negative charges. When the rod is withdrawn, the electroscope remains charged due to excess electrons. Charging by induction. A positively charged glass rod is brought close to the plate without touching it. The negative charges in the electroscope are attracted and get concentrated on the metal plate. The leaves are left positively charged due to repulsion by the glass rod, so the leaves diverge. When the metal plate is asked by touching, the leaves collapse. And this is because electrons from the ground rushes up and neutralizes the positive charges in the leaves. So the leaves are neutral. The negative charges at the metal plate are bound there as long as the glass rod remains closed. When the glass rod is removed, the electrons redistribute and the leaves diverge due to repulsion. So the electroscope acquires a negative charge. In the same way, an electroscope can be charged positive by bringing a negatively charged rod near the metal plate. It repels the negative charges downwards, causing the leaves to diverge. The positive charges are bound at the metal plate due to attraction to the negatively charged metal rod. Earthing causes the electrons to flow from the electroscope to the ground and the leaves collapse. When the charged rod is withdrawn, the positive charges redistribute and the electroscope is positively charged and the leaves diverge due to repulsion of the positive charges. Next, uses of an electroscope. Now, we've already seen that an electroscope can be used to detect whether a body is charged or not. In fact, it can also be used to detect the type of charge on a charged body. For example, if a charged body is brought close to the plate of a charged electroscope and the leaves diverge further, the body has the same charge as the electroscope. But if the leaves diversion decreases, then the body has an opposite charge to that of the electroscope. And finally, we look at the applications of electrostatics. And we start with electrostatic precipitators. Now, the carbon and other dust particles released in the atmosphere from industries are removed by electrostatic precipitators. In this method, two electrodes are fitted against the inside wall of a smokestack. When a high voltage is applied, an electric discharge takes place across the stack, and as a result, air in the stack is ionized. The ionized air consists of ions and free electrons. The free electrons gets attached to the gaseous particles moving up the stack. The particles get negatively charged and are attracted to the positive electrode located on the inner wall of the stack and settle down there. This can be dislodged from the electrode by vibration of the electrode and are collected in a reservoir. In this way, about 99% of the particulate matter gets removed from the fuel gases by this process. Secondly, spray painting. Now, electrospray starts when a liquid formulation is pushed down a capillary at a precise and constant flow. When an electric field is created by wiring the liquid to a high voltage, the meniscus rapidly turns into a stable cone, after which a jet of liquid emerges and becomes a stable spray. Highly charged droplets are formed in the jet due to electrostatic repulsion. They break into finer charged droplets, which themselves break into smaller and smaller ones. Finally, the photocopier. A photocopier consists of a halogen lamp, a photosensitive drum, a toner, and a conveyor belt. When you place a document you want to be copied upside down on the glass and press the start button, an intense beam of light scans across the document from top to bottom. This light then gets reflected and falls on the photosensitive drum. This photosensitive drum is a metal roller which is electrostatically charged by a high voltage wire. It is coated with a photosensitive chemical called selenium, which is a semiconductor. So it acts as an insulator in dark areas, and when light falls on it, it conducts electricity. So, when a beam of light scanned across the document, light gets reflected from the white areas, while the printed letters, being black, do not reflect any light. When this reflected light falls on the photosensitive drum, the areas of the photoconductor which was exposed to light becomes conductive and gets discharged, whereas the areas of the drum which were not exposed to light remains negatively charged. And therefore, we get an electrical shadow of the page on the photosensitive drum. So as the drum rotates, it carries the electrical shadow towards the toner. The toner is positively charged, so the toner particles stick to the electrical shadow which is negatively charged. And so an image of the page is formed on the drum. Then a blank sheet of paper is fed from the harbor. As it moves along, the paper is given a strong electrical charge. Thus, the toner image is transferred from the surface of the drum onto the paper. The paper then passes between two hot rollers. The heat and pressure on the rollers permanently fuses the toner particles on the paper.